Hello everyone, welcome back to LMJ, and today we'll be covering the Electrostatics PYQ from NSEP from the year 2003 to the year 2024. So don't forget to like and subscribe and let me know which chapter do you want next. I am planning to upload one chapter from class 12, then one chapter from class 11. Let me know if this is fine. So next chapter I am planning to upload is laws of motion. So let's begin. The first question is, two small spheres, each of mass m and with a charge q, lie inside a non-conducting smooth hemispherical bowl of radius r. It is something like this. This is the center, and two small spheres of each of mass m and q are lying on the sphere. And they are both in equilibrium. So we have to find the charge. So both have mass m and charge q. So let us draw the forces on each one of them. Electrostatic force will be acting this direction and this direction, and both will have the same magnitude, which is kq square, and separation is d, so d square. Mg will be acting downwards and normal will be acting perpendicular to the surface at this point, so somewhere here, and normal always passes through the center of the circle, so it will be passing through here. This distance is d by 2 and this is r. This we will be using later. So now let us write the equilibrium equations. This was normal and this is theta. So n cos theta can be written equal to q square by 4 pi epsilon naught d square, because in horizontal direction the particle is in equilibrium, and in vertical direction n sine theta is equal to mg. Now normal is a normal and theta are unknown variables, so we need to eliminate one of them. So we can easily eliminate normal by dividing these two equations. So we will get tan theta is equal to, no sorry, tan theta is equal to mg 4 pi epsilon naught d square divided by q square. So from here we need to find the charge, and from here we can use the fact that this theta and this triangle and this is 90 degrees. So this side will come out as r square minus d square by 4 using Pythagoras. So tan theta can be written as r square minus d square by 4 divided by d by 2 is equal to mg multiplied by 4 pi epsilon naught d square divided by q square, and we need to find q, so q will become mg 4 pi epsilon naught d cube by 2 multiplied by r square minus d square by 4 whole root, because we had q square over there and we have to write q. So this is the final answer. Let me simplify it a bit more. It will become mg 4 pi epsilon naught d cube divided by root of 4r square minus d square. So this is the final answer for question 1. It was a 12-mark question. It was fairly simple. And moving on to question 2. A system consists of two metallic spheres of radius r1 and r2 connected by a thin wire and a switch S as shown. Initially S was open and the spheres were carrying charge q1 and q2, and then it is switched closed. So we need to find the potential of the system. So when the switch is closed, both the spheres will come to equal potential because there is no resistance in between of the wire. So if there is no resistance, then by Kirchhoff law you can say that these 2 points should have equal potential because uh, there is no resistance in between them and they are connected by a wire. So let us assume that after closing, the charges become q1 dash and q2 dash. So one equation we have is q1 dash by 4 pi epsilon naught r1 is equal to q2 dash by 4 pi epsilon naught r2. So this is one equation, and the second equation is of charge conservation because the total charge should be equal before and after closing the switch because charge is not going anywhere, it is on the system only. So q1 plus q2 is equal to q1 dash plus q2 dash. So now we have two variables q1 dash and q2 dash and two equations, so we can solve for q1 dash and q2 dash. So for solving, I can write q2 dash as q1 plus q2 minus q1 dash, and I will put this in first equation. So this will become q1 dash by r1. I've cancelled out 4 pi e naught on both sides. q1 plus q2 minus q1 dash divided by r2. So from here we will get, I'm taking q1 dash on this side because we need to find q1 dash in terms of q1 and q2. So q1 dash 1 by r1 plus 1 by r2 is equal to q1 plus q2 divided by r2. From here I will get q1 dash is equal to q1 plus q2 by r2 multiplied by r1 r2 by r1 plus r2. So now we need to find the potential of the system, which will be given by kq1 by r1, right? So 1 by 4 pi epsilon naught r1 I am cancelling, so q1 plus q2 by r1 plus r2. So this is given by option B. Moving on to the third question, it says two identical conducting balls having positive charges q1 and q2 are separated by distance r. If they are made to touch each other and then separated to the same distance, the force between them will be. Okay, so here we had q1 and q2 and both had different radius, but in third question we have the same radius. So I'll use this relationship from the first question in the second, from the second question in the third question. So we know that q1 dash is equal to q1 plus q2 by r1 plus r2 multiplied by r1, right, from this thing, and from here r1 is equal to r2 because the conducting balls have are identical. So q1 will be this, and similarly q2 dash, by symmetry I am writing q2 dash will be given by q1 plus q2 by r1 plus r2 multiplied by r2. but here R1 is equal to R2. So let me first write Q1 dash. Q1 dash will be Q1 plus Q2 by 2, right? Because this will be 2R multiplied by R. So R will get cancelled, so by 2, and is equal to Q2 dash. So the force between them was earlier it was K Q1 Q2 by R square, and force after has become K Q1 plus Q2 whole square divided by R square. So now we need to compare between Q1 Q2 and Q1 Q2 whole square. Sorry, there will be a 2 also. Right. So we can prove that we know that AM is always greater than GM. So that means that Q1 plus Q2 by 2 will be greater than Q1 Q2. So this implies that Q1 plus Q2 by 2 whole square is greater than Q1 Q2. So we get the answer as more than before. You can also do this by putting random values of Q1 and Q2, because it should satisfy always, because it is single correct now. So you can put any value of Q1 and Q2 and check which one is greater, Q1 Q2 or Q1 plus Q2 by 2 whole square. So moving on to question 4. If a good conductor is connected between a point of an electric circuit and the ground, then we have 4 options. Current flows from the point to the earth. So this is not true, because imagine this is the conductor and this is connected, this is the point which is connected to the earth. So this circuit is open, so the current cannot flow anywhere. Even if this thing was not open and this was closed, something like this, then also we cannot say that the current will flow from the point to the earth, because it depends on the potential of this point, because earth we always take as 0 potential, and if this is positive potential then the current will flow from this point to earth, but if this is negative then this will be higher potential, so current will flow in this direction from earth to conductor. So option A is clearly wrong. So option B says the potential of the point is same as that of the earth. Right. Since we have connected both the points, so this will eventually become 0 potential, because there is no resistance in between them. So this will become equal to this potential. So this is correct. And third option says current flows through the conductor if and only if one or more point of the same circuit with some resistance between the two is connected to the ground. This is correct, because we know that for the current to flow, we need to have a closed circuit with some resistance between them, so that there is potential difference between this point and this point, right? Sorry, between this point and this point here, between resistance, then only the current will flow. So connecting one more point to close the circuit is important with some resistance. So option C is also correct. Option D says when the current flows through the conductor to the earth, the current through the circuit remains unchanged. So no, this is not correct, because eventually the potential of this point will keep changing, right? So if this is VA and this is VB, and we know that from Ohm's law delta V is equal to I into R, so VA minus VB is equal to IR, right? And Sorry, I should have taken a point over here somewhere. Imagine this is VB. So VA minus VB is equal to IR. So, and VA is changing. So VA minus VB by R is also changing, right? Because this potential will continuously try to become equal to this earth potential, so VA will be constantly changing. So D option is wrong because current will not be constant. Moving on to question 5. Question 5 says 3 charges Q, 2Q and 8Q are to be placed along a 9 centimeter long straight line so as to make the potential energy of the system minimum. Find the position of the charges and determine the strength of the electric field at the point of Q. Okay, so I need to make the potential energy minimum of the system. So since there are 3 charges and we need to make 2 combinations, we need to take 2 charges at a time for the potential. So we will have 3C2, which is 3 terms in potential calculation, and those 3 terms will be KQ 2Q divided by some distance R1, K 2Q 8Q R2, and KQ 8Q R3. So since this numerator is the biggest, so R2 needs to be maximum to make the whole fraction small. So R2 needs to be maximum, and the maximum length possible is 9 centimeters. So this will be 9 centimeter. Okay. Then this is the second largest numerator. So this R3 needs to be second maximum, right? So let me first put 2Q and 8Q at the ends of the line. So imagine 2Q is here and 8Q is somewhere here. So R3 needs to be maximum, right? So Q needs to be here somewhere, and this will be the maximum thing, maximum distance. So if this is D, then this will be 9 minus D. So I need to make the potential minimum now, right? So 2KQ square by 9 minus D plus K 8Q square divided by D plus 16Q square divided by 9. This is the potential, and I need to make this minimum. So I will take the derivative in terms of D. So this will become, since this is constant, so derivative will be 0, and this has 9 minus D. So minus of 2KQ square 9 minus D whole square minus of, no sorry, this will become plus because there is one more minus over here. So minus of 8KQ square divided by D square. This should be equal to 0 for minimum. So this will give us 2KQ square D square minus 8KQ square 81 plus D square minus 18D. So instead of doing this, we can simply do this. I can take this term there, so this will become 1 by 9 minus D whole square is equal to 4 by D square, and then I can take the root. So 1 by 9 minus D is equal to 2 by d. So this will give us d is equal to 18 minus 2d. So d will come out as 18 by 3, which is 6. Note, when I'm taking the root, I'm not missing any value of d, because d is equal to 0 is either way is not possible. So d will come out as 6 centimeter. So the configuration will be something like this. If this is 0 comma 0, then this will be 3 comma 0, because this was 9 minus d, which is 3, and this will be 9 comma 0. So distance between this and this is g, which is 6. And now this is the a part done. So this is a part, and now I do need to do b part, which is determine the strength of electric field at position q, and that is very easy, and you will get that at q it will be 8 kq square by 6 square, which is 36, minus of 2k q square by 9. So this can also be written as 2 by 9, so we can see that it is equal to 0. So moving on to question 6, it says 3 concentric spherical shells have radius r, 2r and 3r with charges q1, q2 and q3 respectively. Innermost shell and outermost shell are earthed. Then, so let me draw. This is r, this is 2r, and this is 3r. So now we know that the innermost shell and outermost shell are earthed. So this is earthed and this is earthed. So now the potential at these two shells will be 0. So I can write the equation. So I am writing for innermost first. So this one will be and for outermost shell I can write as so this will give us, on cancelling out the common terms, we will get q1 plus q2 by 2 plus q3 by 3 is 0, and also q1 plus q2 plus q3 is 0. So first we need to find the relation between q1, q2 and q3. So we can see that q1 plus q2 will be equal to minus q3, which is option A. So option A is correct. Sorry, this was q3 and q2. Then we need to find relation between q1 and q2. So I will find q3 in terms of q1 and q2, which is, so q3 will be equal to minus q1 minus q2, and I will put this in the other equation. So we will get q1 plus q2 by 2 minus q1 by 3 minus q2 by 3 is 0. From here I will get 2 q1 by 3 minus of q2 by 6 is 0, which will give us q1 by q2 is equal to 1 by 4. So sorry, this will be plus This is option B, so option B is also correct. And similarly, on eliminating Q2, you'll find that option C is also correct. I'm leaving this as an exercise. So question 6 has answered ABC. This was a 6-mark question from 2005. So moving on to question 7, we have a thin non-conducting ring of radius r is placed in the xy plane. The charge is distributed along the ring with density lambda is equal to lambda naught cos theta, where a is a constant and lambda naught is the angle made by radius vector with the positive direction of x. So we need to find the electric field intensity at the center. So let me make the ring first. So this is the ring, and this is the positive x-axis, and this is theta. So in the first quadrant, cos theta is positive. So the charge distribution will be something like this: maximum over here, and then it will tend to 0. So I'm putting more distance between the plus charges, and then it will start becoming negative. So most negative it will be here, then it will also start decreasing, and cos theta is positive in the fourth quadrant, so it will start becoming positive, right? So we need to analyze the field at the center. So we can see that due to this whole positive thing, the in y axis the positive fields will get cancelled, right? Because if this is the field from here and this is the field from here, then these two will be equal if I'm taking the same theta and minus theta. So this component will get cancelled, right? And only we will get this component. Similarly for negative also, the field will be in this direction only, because negative is an attractive. We will get the field in this direction only, and both the components will get cancelled. So we will have only x component of the field. So the field will be directed in the minus x direction. So now let me write the field due to some very small element d theta, this thing. So due to this, we will have the field here, right? And this will be dE. So dE can be given as k dq by r square, and dq can be given as, first we need to find the linear charge distribution, which is given as lambda naught cos theta. Then this length will be given as r d theta and divide by r square. So 1 r will get cancelled. Then since this is d is an vector quantity, so we cannot directly integrate this, because vector also has a magnitude and also has a direction. So we can integrate in only the same direction. So since we know that the field is only in the x direction, so we can take the x component and integrate. So this angle will also be theta because of the opposite angles. So dE cos theta will be given as k lambda naught cos square theta d theta divided by r. So now we need to integrate this from, the angle is starting at 0 degrees and it will move whole circle, so this will be 2 pi. So integrating this, This will be, we don't know the integration of cos square theta, so I will use some trigonometric properties. K lambda naught, I can write this as cos 2 theta plus 1 by 2 d theta divided by r. So now this will become plus of d theta by 2 from 0 to 2 pi, right? So now this will become k lambda naught by r, and integration of this will be sine 2 theta by 2. So this will become k lambda naught by r, and sine 2 theta naught at 2 pi is sine 4 pi, which is 0, and sine 0 is also 0. So this term will become 0. And we have pi from here. So final answer will be k lambda naught pi by r. So this was a 12 marker question, and this is very common question, and you will find it in Erodov also and many coaching modules. So question 8 says 4 identical charges are placed at 4 vertices of a square lying in YZ plane. A fifth charge is moving along x-axis. The variation of potential energy along x-axis is represented by. Okay, so the situation is something like this. Imagine that this is the y-axis, this is the x-axis, okay, and this will be the z-axis by right-hand rule. So now the charges are placed something like this, right? This is Q, this is Q, this is Q, and this is Q, and we need to find the potential at along the x-axis. So I am finding the potential at a random point on x, so I can find the relation between the charges and the x-axis, x coordinate. So take at any random x comma 0, so at any random point x comma 0, so potential at this x comma 0 can be given by kq by r due to any one charge. So due to any one charge, this will be the r will be this, right? And since this is a 3D r, so it is a bit difficult to visualize it, so I will give you another method. We can write this like this. So we need to find the modulus of x minus L by 2 and minus L by 2. So this will be equal to x square plus of L square by 4 plus L square by 4, so L square by 2. And since, always remember that potential is not a vector quantity, it is a scalar quantity, so there is no direction, so we don't need to take any cos or sine theta, so we'll just multiply it by 4 because of the symmetry. The potential due to each charge will be this only, so we'll multiply it by 4. So this is the equation of the graph, and so let us check one by one. So when x is 0, so the potential will be some finite quantity, right? So option A and option C are wrong, and option D also, there is no finite quantity at 0. So option B is the only option remaining, and we can also see that it will be symmetrical because the negative charge won't, negative sign won't matter because this is inside square root and this is being squared. So it will be symmetrical, this is symmetrical. And also it will be decreasing because denominator will increase as we increase x. So B is the best answer possible. A particle having a mass m and charge q moves along a line under the action of an electric field E is equal to alpha minus beta x, where alpha and beta are positive constants and x is the distance from a point where the particle was initially at rest. Then for an observer moving with an acceleration q alpha by m. Okay, so NSEP has solved this question without considering the observer, because if we consider the observer, then none of the options will come out as true. So I will also be ignoring this last line. So we are given that E is equal to alpha minus beta x. So force will be equal to Q multiplied by E, which is Q alpha minus beta x. This will give us acceleration is equal to Q by m multiplied by alpha minus beta x. So we can write acceleration as d square x by dt square. And if we rearrange the terms, we will get right. So this is a second order differential equation and this is non-homogeneous. Non-homogeneous means that the right hand side of this equation is not equal to 0. So when it is equal to 0, it is known as homogeneous equation. So, and when it is equal to 0, it will become the standard equation of SHM that we know the solution to, but we don't know the solution to this equation. So solution to non-homogeneous differential equation is given as the solution to corresponding homogeneous equation, homogeneous differential equation plus a particular solution. Right, so first we'll find out the solution to the homogeneous part. And I'll denote it by XH. So we will get d square x by dt square. This is the homogeneous equation, right? And we know the standard solution to this equation is of the form we read this in SHM basic theory. Right, and Now for the particular solution, there are some rules for finding the particular solution. I will represent it by xp bracket t. So xp depends on RHS of non-homogeneous differential equation. Since here RHS is a constant, so this implies that the particular solution is also constant. This we have to remember. Okay, always when the RHS is a constant, then the particular solution will also be a constant. So putting the xp in the original equation, we will get we had this so cancelling out the common terms, we get that the particular solution is alpha by beta. So the final combined solution will become so since we had x is the distance from where the particle was initially at rest. So if we take the initial position to be at origin, then we'll get that at t is equal to 0, the particle was at origin. So x at time is equal to 0 was 0. This will imply that a plus alpha by beta is equal to 0, which will give us a is equal to minus alpha by beta. Now the particle was at rest at t is equal to 0, so velocity will be 0. So this will become so this implies that b is also equal to 0, right? So xt becomes, since a had minus alpha by beta and this is also alpha by beta, so we can write it as alpha by beta 1 minus cos of omega t, where omega is q beta by m root. Sorry, this was b only. So from here we can match the options. We can see that the equation that we obtained for the position is equation of SHM. So a option is correct. Amplitude was also alpha by beta, because the limits for cos omega t is minus 1 and 1. So this xt will range from 0 to 2 alpha by beta, and in between there will be a mean position also. So if we take the half of 2 alpha by beta, we will get the amplitude from the mean position. So B option is correct. The mean position of particle is at x is equal to alpha by beta. Mean position is when the acceleration is equal to 0. So that implies that force is equal to 0. So alpha minus beta x should be equal to 0. That gives us x is equal to alpha by beta. So option C is also correct. And maximum acceleration is asked. Maximum acceleration is given by amplitude multiplied by omega square. So this will become alpha by beta multiplied by qb by m, which will give us alpha q by m, which is option D. So D is also correct. So this was a nice question, 6-marker question. So ABCD is the answer. Moving on to question 10, we have a long thin rod AB is charged uniformly. The electric field at point C is directed. So we need to find the direction of the electric field due to a long thin rod at any point C above it. So let me draw some angles. Let this be theta 1 and this be theta 2. So we know that the x component of field is given by kq by lr multiplied by cos theta 2 minus cos theta 1, and ey is given by kq by lr sin theta 1 plus sin theta 2, right? So ex will be positive because theta 2 is smaller than theta 1. So cos theta 2 will be greater than cos theta 1. So this is positive. So it will be ex will be in positive x direction, and ey will be also in positive y direction. So the field will be somewhere along. Let us assume that the field is somewhere here, and it is clearly not parallel to the rod. So A is wrong and B is also wrong because it is not clearly perpendicular to the rod. So let us analyze C. It says that the field is directed along the bisector of ACB. So this is ACB angle theta 1 plus theta 2. So if this bisects it, then this angle should be theta 1 plus theta 2 by 2. And this whole angle should also be equal to this whole angle should, sorry. This whole angle should also be equal to theta 1 plus theta 2. Right. Let me mark these points. So this triangle that we have, this angle would be equal to theta 1 plus theta 2 by 2 minus of theta 2, because this angle is theta 2. So if we subtract this from this whole angle, this will become theta 1 plus theta 2 minus theta 2. So this will be, and this is equal to theta 1 minus 2 theta 2. And this is a 90-degree angle. So if angle MCN is equal to theta 1 minus theta 2, then C is correct, right? So angle MCN can be written as pi by 2 minus of angle CMN, because the sum is 180 degree and this is 90 degree, is equal to theta 1 minus theta 2. This we have to verify. So we need to find CMN angle, and we know that this is the field that we have extended. So Ex is in this direction and Ey is in this direction. So angle CMN can be given as tan inverse of Ey by Ex, right? Let us substitute the values of Ey and Ex. Cancelling out the common terms, we get so let us, sorry, this was sine, exchange the terms by mistake. So this will be sine theta 1 plus theta 2, and this will be cos theta 2 minus cos theta 1. So this will become 2 sine theta 2 plus theta 1 by 2 cos theta 2 minus theta 1 by 2, 2 sine theta 2 plus theta 1 by 2 sine theta 1 minus theta 2 by 2. So 2 sine theta 1 plus theta by 2 is common, so cancel it out. So you will be left with tan inverse cot theta 1 minus theta 2 by 2, because you can take the negative, and cos negative theta is also cos theta. So let us verify here that pi by 2 minus of tan inverse cot theta 1 minus theta 2 by 2 is equal to theta 1 minus theta 2 by 2. Now cot theta is also written as cot pi by 2 minus tan pi by 2 minus theta. So we can write this as pi by 2 minus theta 1 minus theta 2 by 2. So this will become theta 1 minus theta 2 by 2 is equal to theta 1 minus theta 2 by 2, hence verified. So option C is correct. This was a nice question. Now moving on to question 11, we have an electric field is given by E is equal to y iota cap I cap plus x j cap volt per meter. The work done in moving a charge 10 microcoulomb from a point R1 to R2 is. So work is given by minus of E dot dr from R1 to R2. So this will be given as dr can be written as dx I cap plus dy j cap from 3,4 to 2,6. So this will become y dx plus x dy from 3,4 to 2,6. So this will become, we know that y dx plus x dy is the differentiation of xy. So we can write this as xy differentiation. So on integrating, it will become xy from 3,4 to 2,6, which will give us 12 minus 12, which is 0. So the answer is D option. Moving on to question 12, we have a charge 6 microcoulomb is situated inside a closed surface. The flux in volt meter through a portion of the surface subtending a solid angle of pi by 2 at the point where the charge is situated is. So we know that total flux due to charge is given by Q by epsilon naught, where Q is the charge, and total angle subtended by closed surface is given by 4 pi. So flux through surface subtending unit angle can be given as q by 4 pi epsilon naught. So by unitary method we will get that flux through surface subtending pi by 2 angle is since q is 6 microcoulomb, which will give us 0.75 by epsilon naught multiplied by 10 raised to power minus 6. So option D is correct. Moving on to question 13. This is a 12 marker question and this is a good question. Identical thin rods of length 2L carry each charges plus Q uniformly distributed along their length. The rod lie along x-axis with their center separated at a distance A, which is greater than 2L. So the rods are not intersecting. Show that the magnitude of the force exerted by one rod on the another is given by. So let me draw the situation. There are two rods. If this is at origin, this will be at 2L comma 0 because the length of the rod is 2L and the length of the origin from center would be L. So this is L comma 0. And since the centers are at a distance A, so this will be L plus A comma 0. And if we subtract L, we will find the coordinate of this point A comma 0 and this will be 2L plus A comma 0. So we need to find the field due to this rod on this rod, the force. So first I am assuming a charged element of this rod and I am assuming the charge to be B, and this is at a distance of C from the left end of the right rod, and then I am assuming a charged element on this rod at a distance x from the left side of the right rod, so this will be dx. So the force due to this thing on this element would be given as F due to B on this dx is given by KB. The charge of this will be given as Q by 2L multiplied by dx divided by C plus x square, right? So the force due to B on right rod will be given as KB Q by 2L multiplied by dx by t plus x square, and if we integrate this x from 0 to 2L, we will find the force due to B on this entire rod. So we will get minus of KBQ 2L 1 by C plus x from 0 to 2L. So this will give us one by C plus 2L. Sorry, this will give us 1 by C minus 1 by C plus 2L, right, which will further give us KBQ by 2L multiplied by 2L C plus 2L. 2L gets cancelled, so this will give us KBQ by C plus 2L, right? Now we need to find the force due to this entire rod on this entire rod. Now we have already found the force due to an element of the left rod on the entire right rod. So let us draw a new situation. If we take an element at a distance x from the origin, so we know that the distance between the right end of left rod and left end of right rod is a minus of 2l. And this will be given as L minus of x, 2l minus of x, because this whole length is 2l and this is x. So this will be given as 2l minus x plus a minus 2l, which is a minus x, which is also equal to c from the above diagram, right? Because c was this distance and this is also this distance. So we can write the force due to dx on a right rod. I am using this equation which we derived earlier. It will be given as k, and now we cannot write it as b because I have not assumed it as b. Q by 2l dx multiplied by q divided by c, which is a minus x, and c plus 2l, which is a minus x plus 2l. So now we can integrate this from 0 to 2l to cover this entire left rod. So this will become kq square by 2l. Now to integrate these kinds of equations, we have a trick. You might have used it in maths if you have studied the differentiation integration chapter. So this will become, if we add another 2l square, if we multiply 2l in the denominator and also 2l in the numerator, so we will get this. And why I have done this? Because the difference of the this term and this term is constant, which is 2l. So we can write this as a minus x plus 2l minus of a minus x, which is the difference is 2l. So now this will become we are cancelling out the common terms. Right, we will get this, and this is easy to integrate. We know the integration, which is log. So this will become minus of this from 0 to 2l, and minus minus will become plus. So now this will become kq square by 2l square whole square, 2l whole square, and first we put 0 because there is minus, so log of a, then we put 2l, so a minus 2l, plus of, first we put 2l, so this will become log of a divided by a plus 2l, which will give us kq square by 2l whole square log of a square by a square minus 4l square. So this gives us the equation result which is mentioned here. So question 13 was good. Moving on to question 14, we have, when a soap bubble is given an electric charge, it contracts, it expands, size remains same. So we need to comment on the size. So let us draw a soap bubble. And the soap bubble has a charge density of sigma. So let us analyze a patch with surface area ds. So we need to find the force on this patch due to the entire rest of the bubble. So let us do that. Assume that this is the rest of the bubble and this is the patch. So the force due to the rest of the bubble here will be, I am assuming it to be E2, and here also it will be E2 in the same direction, because these 2 points are inside and outside of the bubble, but they are very close to each other and there is no obstruction between, so the field will be same. And here I am assuming it to be E1, and here it will be E1 in this direction, and the field inside the bubble should be equal to 0 because of Gauss law, because this will not contain any charge inside. All the charge is residing on the surface. So this will become E2 minus of E1 is equal to 0 if I am taking this direction as positive. And E outside, we already know that outside it is given by lambda by A E naught. We know by Gauss law. So E1 plus E2 is given by sigma by A epsilon naught. So on eliminating E1 from here, we will get E2 is equal to sigma by 2A epsilon naught, and E1 is equal to sigma by 2A epsilon naught. So the force on ds would be equal to dq multiplied by E2, because E2 is the field which will be acting on this patch if this patch was removed. So we need, and also we consider the field due to all the charges other than the charge which the field is acting on. So this will be equal to multiplied by lambda 2A E naught. So this will become lambda square ds by 2A E naught. So the force per unit surface area will be equal to which is acting in the positive direction, which is this direction. So the bubble will expand in size and it won't depend on the charge, because we have taken sigma square, so charge will automatically get cancelled. So question 15 says a body is in the form of a right circular cone of dielectric material with base radius r and the height h, and it is placed on a base on a horizontal table. A horizontal uniform electric field of magnitude E penetrates the cone, the electric flux that enters the body. So flux is given by E multiplied by area, and the circular cone will be something like this, right? And this is E. So we need to find the area of this triangle, because the E will be perpendicular to this area, right? I have not drawn it perfectly horizontal because I'm drawing by hand. So area will be given as the area of this triangle. This is 2r and this is h, right? So area is half into 2r into h. So flux is ERH, which is option B. So question 15 has answer B. Question 16 says two identical thin rings, each of radius a, are placed coaxially at a distance a apart. Let charges q1 and q2 be uniformly placed on the ring. The work done in moving a charge q from the center of one ring to the other ring is. So at this point, the potential would be, due to q1, it would be kq1 by a. This is a, and this is also equal to A. KQ1 by A plus KQ2 by A square plus A square, right? Because the field due to a ring on a point is given by KQ by root of radius square plus distance square. So A square plus A square, which will be KQ1 by A plus KQ2 by root 2A. Similarly, this potential would be KQ2 by A plus of KQ1 by root 2A. By symmetry, I have written this. So work done would be minus of potential, which is minus of change in potential. So this would be given, this would be written as so this we can write as K by A Q2 1 minus 1 by root 2 minus of Q1 1 minus 1 by root 2. So this will finally give us root 2 minus 1 by root 2A multiplied by 1 by 4 pi epsilon naught multiplied by 1 by A multiplied by Q2 minus Q1. So this is, sorry, I forgot to include this minus sign. So this is given by option C. So question 16 has option C as answer. Question 17 says two conducting plates A and B are placed parallel to each other at a small distance between them. Plate A is given by charge Q1 and plate B is given by charge Q2 then. So assume that this is plate A, this has charge Q1, and this is plate B, this has charge Q2. So I need to find the distribution of charge on the inner and outer surface. So let me assume that on the inner surface the charge is Q1 minus Q. So since they are at small distance, so all the flux which is given out by this Q1 minus Q charge would enter this inner surface of B. So the flux charge on it would be minus of this charge, which is Q minus Q1. And since the charge on this needs to be conserved, so the sum of inner and outer charges should be Q1. So this will be Q. Similarly, the outer charge would be Q2 minus Q plus Q1. And since a point inside A inside a conductor, the field is always equal to 0. So let us analyze. So since these two charges are opposite and the distance is minimal between them, so we can consider the contribution of these two charges as 0 because they are equal and opposite. So due to Q there will be charge here, and due to this charge, this thing, there will be a field here. Which will give us that Q is equal to Q1 plus Q2 by 2 and Q2 minus Q plus Q1 is also equal to Q1 plus Q2 because it is equal to Q. So we find out that outer surfaces of A and B get the same charge and polarity and of magnitude this is correct, and they have opposite signs and the magnitude would be same, and if we calculate q minus q1 it will come out as this only. So option C is also correct. So moving on to the next question. Question 18 says a plastic ring of radius r has a charge 3q distributed uniformly along 1/4 of its circumference and a charge minus q distributed along the rest of the circumference. This is 1/4. It has 3q and the rest has charge minus q. We need to find the potential at a distance of √3r. So the points on which this 3q charge has been distributed, each point will have a distance of, by Pythagoras we will get this as 2r. So each point will have a distance of 2r. So the entire 3q charge can be imagined to have a distance of 2r from the point. So the potential can be written as k3q by 2r. And similarly for minus q we can write it as kq by 2r. So this will give us 2kq by 2r, which is kq by r. So option C will be correct. So don't get confused that you have to divide this thing by 4 because it is distributed only on quarter surface. No, each point has the same distance, so we can directly write it as this. So question 19 says the figure shows 4 orientations at angle theta with a magnetic field B of magnetic dipole with moment m. The magnitude of torque and potential energy is best represented by. So we need to comment on torque and potential energy. Torque, we know that it is given as mb sine theta, and u is given as minus mb cos theta. Okay, so let us analyze option by option. Option A says tau 1 is equal to tau 2. So tau 1 and tau 2. So the magnetic moment of 2 and the field have an angle theta, but the moment and field of first dipole have angle of pi minus theta. But we know that the sine pi minus theta is equal to sine theta only. So this thing will be correct. Then we have tau 3 is equal to tau 4. So same, 3 has theta degree with B and 4 has minus pi minus theta. So this is also equal. So and then we have u1 is equal to u2 is equal to u3 is equal to u4. So u1 and u2 they have angle theta and pi minus theta, but cos pi minus theta is not equal to cos theta. Cos pi minus theta is equal to minus cos theta. So this is wrong. So option A is wrong. Now option B says tau 1 is equal to tau 2. We already proved this. This is equal to tau 3. Let us check. Tau 2 has angle theta and tau 3 has minus theta, and so tau 3 has a angle of minus this also has an angle of theta only because m and b have angle theta. So this is also correct, and tau 3 is equal to tau 4 we already proved, so this statement is correct. Remember that this is not minus theta, this is theta only between the vectors. And u1 is equal to u4. Let us check this. u1 has an angle of pi minus theta and u4 also has pi minus theta, so this is correct. Cos will be equal since angle is equal. u2 is equal to u3. This is also correct because both the dipoles have angle theta with the field, so this is correct. So option B is correct. So we need to be careful to not take this as minus theta. Question 20 says, it is a 12 marker question and it is a bit tricky. A tower used for power transmission leaks a current I into the ground. Assume that the current spreads uniformly into the ground. Let rho be the resistivity of the ground and r be the distance from the center of the tower assumed to be a rod. The lower end of the rod is spherical with radius b. So first we need to determine the current density as a function of r. So assume this as the center of the rod and this is some distance r. We know that the current is distributed uniformly hemispherically. So the current density would be given as I by the surface area of this hemisphere. Since the current is distributed hemispherically, so we are taking a hemisphere at distance r and the surface area is given as 2 pi r square. So this is the current density. Then second question says magnitude of electric field at a distance r. We know that J is given by conductivity into electric field. So electric field would be given as J by sigma, which is equal to J multiplied by resistivity. Since 1 by conductivity is resistivity, so this will become I rho by 2 pi r square. So this is the answer for electric field. And then we need to find the potential difference between the lower end of the rod, which is circular, and a point distance r. So we know that potential difference is given by minus of E dr. E we already have and limits would be from B to R, right? Since the lower end of the rod is hemispherical and at a distance of B from and this field is I rho by 2 pi r square and there was minus also, so this would become minus of I rho by 2 pi r from B to R. So minus minus gets cancelled and we put the limits. So this is the answer for third part of question 20. Question 21 is a wrong question because none of the options are matching, but still we will solve it. And this kind of question was repeated in JEE Advanced 2015. The same question with different values. So let us solve this question. Let us assume that this is y-axis, this is x-axis. So this would be z-axis and uniform line charge with density rho is equal to 50 microcoulombs per meter lies along the rod. So this is the rod and this has rho is equal to 50 microcoulombs along the x-axis. The electric flux passing through unit length of the portion of the plane z is equal to minus 3 bounded by y is equal to plus minus 2. So the plane is behind the rod and it is bounded by plus minus 2y and this is z minus 3. So let me draw this figure in another view. Let us assume that this is the line charge and sorry. This is the line charge which is on top of the middle of this plane and this distance is given as 2 and this distance is also given as 2. So this distance becomes 4 and this plane is 3 meters below this line charge because it is at z is equal to minus 3. So this is the length distance which I am talking about, right? So So we need to find the electric flux per unit length crossing the portion of the plane. So per unit length means that we have to take this kind of unit length here, and we need to find the flux due to this line charge. So we know that the field due to this line charge at any point is given by 2kq divided by r, right? So we can write flux is given as dE multiplied by dA. So this will be given as 2k if this point is distance x from the center. So this will be given as 2k lambda by So we need to find the flux through this strip. Let us consider a elemental thing here. So the field here would be given by 2k lambda by r. So 2k lambda divided by, since this is 3 and this is x, so this distance will be given by root of 9 plus x square multiplied by dA, which is given by, so 1 into dx, width of this strip, multiplied by cos theta. So cos theta is this angle, right? So this cos theta would be given by 3 by 9 plus x square. So if we integrate this from -2 to +2, we will find the flux through the strip. So this will be given by 6k lambda tan inverse of x by 3 from -2 to +2 and 1 by a also, so by 3, right? So this would be given by 2 multiplied by 2k lambda tan inverse 2 by 3. So if we calculate this, then we'll find out that none of the options are matching here, because the units are also wrong. So this question is wrong. So you can also do this by forming a cylinder around the charge and by calculating the angle which this thing is subtending, and then we know the flux which 360-degree angle contains, so we can use unitary method. You can find it on Google if you search for the 2015 similar question. So this has no answer. Okay. So now moving on to question 22, we have an infinite number of charges equal to 0.2 mu c are arranged in a line at a distance of 1248 meters from a fixed point. The potential at the fixed point is, if we take the fixed point to be origin, then at 1 comma 0 we have 0.2 mu c, 2 comma 0, 4 comma 0. So the potential will be equal to since K and Q are equal, so 1 by 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. So this is a GP. So it can be written as K into 0.2 mu C multiplied by 1 by 1 minus 2. So this will become K into 0.2 into 10 raised to power minus 6 multiplied by 2, which will give us option C as the correct 3600 volt. You can calculate. Question 23 says two semicircular wires of radius 20 and 10 have a common center at origin O as shown in the figure. Assume that both the wires are uniformly charged and have an equal charge of 0.7 nanocoulomb each. The magnitude of field at common center is given by. So due to a semicircle, we can calculate the field. If this is phi, then this small section will subtend d phi, and field due to it would be here. And you can see that if we take opposite at section at minus phi from here, so it will also subtend in this direction. So y components will get cancelled for the entire semicircle, and there will be field only in the horizontal direction. So this would be dE. This is 90 minus, sorry, this is phi. So this is dE sine phi. So dE sine phi can be written as K into dQ can be written as Q divided by pi r, since the total length of this semicircle is pi r, into r d phi. The length of this small is given as r d phi multiplied by sine theta whole divided by r square. So this will become r cube, and we can cancel 1 r from here. So this will become, if we integrate this from 0 to pi, we will cover the whole semicircle. So this will become kq sine phi d phi by pi r square, which will finally give us that kq pi r square cos phi from 0 to pi, and there will be minus sign also. So this will become k cube pi r square multiplied by 2. So now we need to find the field at common center. So it would be given by 2k, and they have equal charge, so q is common, by pi. And since this radius is small, so denominator will be smaller for this, so the field will be in this direction. So 20 and 10 are the radius, so this will give us the answer as 301 volt per meter. You can calculate. So moving on to the question 24, we have electric potential in a region along the x-axis varying with x according to the relation 5 plus 4x square. Therefore, so we know that they are asking the potential difference. So V minus 3 minus V1, this will be given as 5 plus 36 minus of 9. So this will become 27 plus 5, which is 32 volt. So A is correct. The force experienced by a charge of 1 coulomb place at x is equal to -1 is, so force is given as minus dv by dx. So this will become minus 8x. So force at x is equal to -1, it will be 8 Newton. So B is also correct. Force experienced by the above mentioned charge is along positive x-axis, right? Because this is positive, so this will be along positive x-axis. Uniform electric field exists in this region along the x-axis. No, this is wrong because this field is not uniform, so this will be wrong. So answer is ABC for question 24. Two identical metal spheres of density rho, this should be rho, having equal and similar charges are supported from a common point by means of a silk thread of length L and negligible mass. Two threads make an angle 2 phi with each other when in equilibrium in air. When the same system is immersed in a dielectric liquid of density sigma, then the angular separation changes to 2 phi 2, 2 theta 2. Find the relative permeability in terms of this, and in case of angular separation remains unchanged, so theta 1 is equal to theta 2, then we need to find a dielectric liquid relationship for this epsilon L. Okay, so let us draw the situation before and after. So before, the situation is like this. The electric field will be in this direction and mg will be downwards. So this, writing the equations of equilibrium, we have T sine theta 1 is equal to kq square by r square. So this will be equal to 1 by 4 pi epsilon naught q square by 2l sine theta 1, because this will be L sine theta 1 and this will be 2L sine theta 1, and T cos theta 1 is equal to mg. So tan theta 1 will be equal to q square by 4 pi epsilon naught mg 4L square sine square theta 1, and after this, after emerging in the liquid, this will become buoyant force will be upwards, tension will be here, mg will be here, and electric field will be here. So in vertical direction we can write tension will change, it will not remain same. So T sine theta 2 is equal to, in x direction I am writing 1 by 4 pi epsilon naught q square by, since length remains same and theta has changed, so in y direction it will become mg minus b. So finally tan theta 2 will be given as q square by, and this will be epsilon r also, because in liquid there will be relative permeability also. In air the relative permeability is equal to 1, so we do not consider it, but in liquid we will have to consider it. So now we need to find out the relative permeability in terms of sigma, pi, rho, theta 1, theta 2. So we can find out that tan theta 1 by tan theta 2 will be given as, we are basically eliminating the common terms q, l. So we can, since we do not need those in our calculation, so this will be right. And buoyant force can be written as we can cancel this, so it will become 1, and buoyant force I am writing as v sigma g, and this is the density of liquid, and if we write v rho g, it will be the weight, right? So now we can write this as 1 minus sigma by rho. So from here we needed to find relative permeability in terms of this. So this will give us relative permeability is equal to one divided by 1 minus this. Okay, so the second part says if theta 1 and theta 2 remain same, then the relative permeability will be equal to. So if theta 1 is equal to theta 2, then these terms will get cancelled out. Then it will become ER is equal to. Okay, so this was the answer of question 25. So moving on to question 26. A charge of plus 2 microcoulombs is situated off center of a hollow spherical metal shell. Then assume this is the outer surface of the shell and this was the inner surface, and plus 2 mu is located somewhere here. So we need to find the distribution on inner and outer surface. So since the so we know that the field inside the conductor should be equal to 0, right? So a charge of minus 2 mu c will be distributed on the inner surface, so that by Gauss law we have 0 charge enclosed inside the circle, right? So now we need to determine whether the charge on the internal surface would be uniform or non-uniform. So it would be non-uniform, because if the charge here is uniform, then charge here and here will be same, but charge due to 2 mu c here and here would be different, so that would not lead to E is equal to 0. So we find out that the charge should be distributed non-uniform according to this 2 mu c, because this is not at the center, so C is correct. And on the outer surface 2 mu c will be distributed, but on the outer surface the charge is distributed uniformly. So option B is incorrect, option A is incorrect. And no charge appears, this is also incorrect. So option C is correct. Long straight wire carries a charge with linear density sigma rho lambda. A particle of mass m and a charge q is released at a distance r from the wire. The speed of the particle as it crosses a point 2r is. So this has lambda density. A particle of mass m and charge q are released at a distance r from the wire. So we can do this by two methods. So first method is the field due to this would be given as at any distance x. So the acceleration would be given as acceleration can be written as v dv by dx. So this will give us v dv is equal to lambda q dx by 2 pi e naught mx, and we can integrate this from r to 2r, and since at r it is released at rest, so v is equal to 0 and we need to find v at 2r. So this will become v square by 2 is equal to lambda q by 2 pi epsilon naught m ln of 2. So v will become equal to lambda q ln 2 pi epsilon naught m root. So this is the first method of doing. This is more of a kinematical method. And second method is related to electrostatics. We will be using the potentials. So second thing can be given as if this is point A and this is point B, so we can write that VA is equal to VB plus half mv square by energy conservation. So this will give us that VA minus VB is equal to half mv square. So this is minus VB minus VA is equal to half mv square, which gives us minus of minus E dr from A to B is equal to half mv square, which will give us 2k lambda by x dx from r to 2r is given by half mv square. So this will give us 2k lambda ln 2 is equal to half mv square, which will finally give us v as so the answer is option B. Question 28 says a charge minus 2q is distributed uniformly on a spherical balloon of radius r. Another point charge plus q is situated at the center of the balloon. The balloon is now inflated to twice the radius. So neglecting the elastic energy involved, find the total electric energy of the system now. So minus 2q is distributed here and plus 2q is here. So initially the energy can be written as right, because this is the self energy and this is the energy due to this minus 2q charge, and finally the energy can be written as this is also equal to 0 and this is also equal to 0, so the change is also equal to 0. So answer is option D. This term was the self energy and this term was due to interaction of the charges. A particle of mass m and charge minus q moves along a diameter of uniform spherical charge distribution of radius r with total charge q. The angular frequency of the periodic motion of the particle is. So we know that the field inside the uniform spherical charge is given as right, and since this is the um, restoring force, so there will be minus charge, and this can be written as minus kx, and k is given by minus m omega square, m omega square, so this will be, so omega will be given as there will be q also because we are writing the force. So the answer is option D.